Okay. One more thing that we can do to our pairwise alignments is at least save a bit on the space. So I've said probably quadratic time we'll have to live with unless you count these logarithmic improvements. But maybe we can at least improve the space, which is also quadratic if you do the dynamic programming in the cookie cutter template way. It's actually very easy if you just care about the final edit distance as a number, because the next, well, you can do it many ways, but you could say the next row that you compute, it depends only on the previous row. So you store these two rows, that's the very maximum you need. And you can, that's clearly enough to compute the final value. So that's bringing the space down to linear. And you can actually do it with a single line if you remember that you also have the dependencies in an orderly way. So you would only depend on this prefix of the previous table. And then the more you move on, the more you can delete. So you depend on the suffix of the previous table. And so you can keep writing the new table here and keep the entries from the previous row in the rest of the array. It's a bit confusing, but it's actually not hard to do. So if you care for the details, they're spelled out here. We have a single row, and depending which index we're currently in at the iteration, the entry is the current row or the previous row. You have to be a bit clever with keeping the entries, the match entry, which is the one that you're currently overwriting. So you have to keep it from the previous one in a local variable. But my point is, conceptually, the two lines would have been fine, and that is trivial to do. Right? There's just no point of keeping the two rows ago in memory if you only care about the final edit distance, the bottom right entry. Now, if we want to do the backtrace, that's not true, right? The standard backtrace needs the entire table, because at each point it asks, oh, where did the minimum come from in the bottom right corner? Fine, I'm going to go diagonally up. Then I'm going to go there and ask, where did the minimum come from? But to do this check efficiently, I have to know the three things that I'm comparing. So there I need the quadratic space, it seems. Anyways, that's true if you use the standard backtracing algorithm as it pops out of the general template. But you can do better here. In a way, it's again, because this dynamic programming problem is so nice and structured and everything, the dependencies are all very local. And the idea is a cool chimera of divide and conquer and dynamic programming. You kind of use the two mixed together. We use dynamic programming to reconstruct the edit script, but we use divide and conquer to reconstruct the edit script, and we use dynamic programming to help us decide how to break things up. So I can try to cut A in half. So I'm going to have my table. Here's A, and there's B. I'm trying to find the optimal path from top left to bottom right, which is some walk here down, something of that sort. It will have to, at some point, cross the middle of A, clearly. So if only I knew this point, I could independently reconstruct the top part and the bottom part. And I can even say this is restricted now to this part of the table, and this is restricted to this part of the table. I might actually never need to look into this ever again. Now, we don't actually know this point in the middle, right? All we've done so far is compute, say, the score in the last row. But we could make that our next target, and we can use dynamic programming for that. This is a standard dynamic programming task. We can separate the problem into several parts, but there's one breaking up point where we have to guess, because we don't know upfront a priori which which breaking point in B we have to use. So we use dynamic programming to compute that one. How to do that? Also, are we now not getting back into the same problem that we need quadratic space to find this middle point? And it turns out no, because finding the middle point you can do with the scores or the edit distances, not the backtrace result. If you want to do it in just the way we've done it so far, then you would need the backtrace, but you can work around in a different way. The best breakpoint in this picture, maybe let me take that. Such a lovely drawing. The best place to make this cut, and this is our J star. It's going to be the best way to go from the top left corner to some point here, and then the best way to continue from there. And these two are summed up. That's the total edit distance. So I have to find the J star that makes that sum minimal. I can do that if I have the entries from here to here, so the edit distance matrix row in the middle. If I have that row, I get all the optimal edit distances from the start on the best path from top left corner to this point. That's what my score already computed. Now for the second part, this doesn't seem to work because we get all possible start points, but the end point is fixed, right? But we can just use the same computation, but reverse the string, reverse A and B. Then what used to be the top left what used to be the bottom right becomes the top left. And we do the same kind of calculation. Edit distance is symmetric anyways. It's the same whether you reverse both strings or not. So there's nothing lost. You could have also written separate code that works backwards. But in the interest of reusing code, I think it's more elegant to write it with the reversed strings. And so that's the final code. There's some boundary conditions, what you do if the first string is very short, and you need that for the recursive call at some point. And this is computing the edit script. So in the notation we've used last time, if the first string is empty, all I can do to produce from the first to second string is inserting all the characters. Likewise, if the second string is empty, I'm deleting all the first characters. If this first string has a single letter, then it's already non-trivial. I have to find the best place to align that character with. So I'm finding the position in B that best matches A according to my alignment score. For edit distance, it would just check if there's an occurrence of the same letter. And then the edit script is getting rid of the first part of B, then replacing the one we found, replacing from A to that letter, and then inserting the rest of B. The interesting bit is if A has some more than 2 letters, then we can do a recursive call, splitting A in the middle. The scores for the top part we compute with just the standard dynamic programming algorithm we've seen so far. For the bottom part, I'm reversing both strings. And then you have to also keep in mind to reverse the indices. So this is a bit of you want to draw the picture and do it. But conceptually, it's the same thing as the top part. And so by just adding those up and finding the best split point, we get our middle point. This point I star, J star is then the midpoint. So the edit script we get from this is the best edit script to get from 0, 0 to I star, J star, plus the best edit script to get from I star, J star to MN. Again, really think of it visually in this graph of points. So you have the 0, 0 up here and the mn down there. There's somehow in the middle, there's your I star, J star. And then it's the best path from here to here and the best path from here to here. Okay. How long does this take? The non-recursive cost, what we do down here, I mean, here we have some linear costs that's dominated by the rest. The main cost comes from these calls to computing rows because they have to fill the entire matrix. They forget most of it straight away, but they still have to compute all the rows one after the other. So these two together have theta nm cost. That's for the computation, but the space remains linear in n, sorry, it's rows. So in all of this, I'm assuming that m is the bigger of the two strings. You can flip that if not. So we get the better of the two, the smaller of the two strings as the space complexity. So this is the part we have to compute in the non-recursive cost. But then I'm also recursing. Now each time I'm making the first string a half as long. So I can have at most log m recursive calls. So a very conservative estimate would be log m times nm, right? That's an n times m. But actually, if you look a bit closer, it's better than that because we get rid of half of the matrix in every recursive call. That's because, again, my picture, if that's your optimal midpoint, the recursive calls only look at this part, and that's precisely half the matrix. So by the standard geometric series, you sum up the full thing, then half the thing, then a quarter of the thing for the recursive calls in total. So the next one, right, will split somewhere here. So again, you're zooming in on a smaller and smaller part. And so the total size of all these parts sums to nm. So the total cost is really nm, which is the same in terms of asymptotic theta class as we had for the more space inefficient version. But we, at all points in time, only just need a single row, or two rows of the matrix. Let's not get too Catholic about this part. Constant number of rows.